Hey, how's it going everyone? Welcome to this video on applications of anti-differentiation. In this video, we're going to have a look at antiderivatives in kinematics, looking at acceleration, velocity, displacement, and what links them between each other. We're also going to have a quick look at other rates of change. So if we recall from the last chapter when we were looking at differentiation, we can find our velocity by finding the derivative of our displacement, dx dt, and same with our acceleration, we can find that by finding our derivative of velocity. So if we go backwards and we're given our velocity and we want to find our displacement, we can find that by finding the antiderivative of our velocity, which is going backwards. And same thing for acceleration. If we're given our acceleration and we want to find the velocity, we just find our antiderivative of acceleration. And that's summed up by this little diagram here. So if we're starting with our displacement, we can find our velocity by finding the derivative of that. If we want to find our displacement and we're given the velocity, we can find the antiderivative of velocity to get our displacement. And same thing over here. If we're given our acceleration, we want to find velocity, we just find the antiderivative of acceleration. Also note that if we're starting with acceleration and we want to find our displacement, we just need to find the antiderivative twice. Okay, so just following the arrows along that diagram. So starting off with a question, we've got work example 5. So we've got a particle moving in a straight line, so its velocity is given by the equation here, 3t squared plus 4t take 4. Initially the particle is 8 meters to the left from the fixed origin, and we want to work out how many seconds does the particle reach, or how long does it take to reach the origin. So we're looking for displacement, we're given our velocity. So as I said before, we're given velocity, we want to find this, so we need to find the antiderivative. So first thing, just need to find our antiderivative of our velocity, and to do that, we add 1 to the power, divide by the new power as normal. And we should get something that looks like this. So 3t cubed on 3, we can cancel out the 3's. 4t squared and 2, so we can simplify that. And the next step, we just need to work out what that c constant is. And we can find that by using this information here. Initially, talking about when t is equal to 0, and it's 8 meters to the left, which means x is 8 meters to the left, so x is minus 8. So if we use those values and solve for c, we'll have 0 cubed plus 2 times 0 squared take 4 times 0 plus c. And if we work that out, we find that c is equal to minus 8. So just rewriting our equation, we have t cubed take 2 t squared take 4 t take 8. And the question asks how many seconds does it take to reach the origin. So what we're doing is we're finding when x is equal to 0. Basically we're finding our time t at x equals 0. So using that information, we find 0 is equal to t cubed take 2t squared take 4t take 8. We just need to solve for t. So factorizing, you can do it by hand or just by a calculator. We'll get t plus 2 squared t take 2. Probably worth practicing just doing it by hand. I'm not going to do it in this video. So that's what we'll end up getting, and then t is equal to either -2 or t is equal to +2, and we can reject t is -2 because we can't have negative time. So our final answer is t equals 2. So the particle reaches the origin after 2 seconds. Part B of the question says calculate the particle's acceleration when the velocity is 0. So again, we've got our velocity is equal to 3t squared plus 4t take 4. And we want our acceleration. Well, that's found by finding the derivative of v. So acceleration is going to be 6t plus 4. We need to find the velocity when it's 0, or the time when the velocity is 0. Okay, so just using this for when v is equal to 0, solving for t. Again, easier to just factorize it. And so we get t is equal to 2 over 3, or t is equal to -2. Again, we can't have negative time, so we can reject that answer. So now using that, t is equal to 2/3 to find acceleration at that time. And we should get t is equal to acceleration is equal to 8. So the acceleration is 8 meters squared, 8 meters per second squared when the velocity is 0. Again, just talking about that little diagram, if we need to find our displacement, if we're given our acceleration to start with, we just need to do it twice, finding the antiderivative twice, and so forth. So we're just looking at acceleration and displacement now. So we've got a particle moving in a straight line, so its acceleration is given by a equals 4 plus 6t. And we've given some initial constraints. If v is equal to 30 and x is equal to 2 when time is 0. So our initial positions and velocity at time equals 0 are these two here. What we want to calculate is the velocity and position when time is equal to 1. So again, to start with, we need to find velocity, and that's by finding the antiderivative of a. So v is the antiderivative of 4 plus 6t dt. So we get 4t plus 6t squared on 2 plus c, and we just need to find out what that is. So using these two information here, well, we can only use this one here at the moment. So v is equal to 30 and t is equal to 0. So we have 30 equal to 4 times 0 plus 6 times 0 squared over 2 plus c. So c is equal to 30. And again, just rewriting it, and I might put the t squared at the front. So that's our velocity, and need to find our displacement as well. So x is going to be the antiderivative of this one. And if we work that out, oops, simplify. And we just need to work out what our constant is, and again we're going to use these two instead. So when x is 2 at time equals 0, and we find that c is equal to 2, and our final step is to find the velocity and position when t is equal to 1. So we do that at t equals 1, so we're just solving for when t is 1. So we get 1 squared is 1, so 3 plus 4 plus 30 gives us 37. And over here we have 1 cubed, 1 squared, and if we add that up, we should get 35. So there's our two answers. Other rates of change, so anti-differentiation can be used to solve other rates of change. For example, if we have an oil spill changing with time, we can find that its area as it changes with time, dA dt, is going to be some function. We can find the area of the spill at any time, and we can find that by finding the antiderivative of that function. So it's just finding the antiderivative of that. And that's what we're going to have a look at in this work example 7. So we've got an ice block with initial volume 36 pi. It starts to melt. The rate of change in its volume after t seconds is given by dV dt equals minus 0.2. Finding the volume in terms of t by using anti-differentiation. So V is going to be the antiderivative of dV dt, okay, which is the antiderivative of 0.2. So V is just going to be minus 0.2 t plus c, and need to work out what that constant is, and we use that by this information here again initially, meaning t is equal to 0. So at time t equals 0, we get 36 pi. So c is equal to, well, just 36 pi. So our volume is minus 0.2 t plus 36 pi. And part B says to calculate one decimal place the number of minutes it takes for all the ice to melt. So when the ice is melted, we have our volume is 0. So we work out when 0 is minus 0.2 t plus 36 pi. And solving for t, we find that t is equal to 36 pi over 0.2, which is 180 pi. So the ice block melts after 180 pi seconds. Divide this by 60 to convert to minutes. So this is in seconds. Need to work out in minutes. So 180 pi divide 60 is going to be about 3 pi minutes. And using a calculator to find one decimal place, we will find that it's roughly 9.4 minutes. So that's all for applications of anti-differentiation. Have a go at the questions. Thanks for watching.